Okay, guys, I borrowed the graphic table from my roommate, so now now we can start. Okay, so we have to compute local and global extrema of this function. So we said before that that the domain is R because there are no restriction about logarithm and denominator and root of even index. And so we start computing the derivative. The derivative was the following one. So cosine of x plus sine of x. And then we had to study the sign of this derivative, and the solution was minus pi over 4 plus 2k pi smaller or equal than x smaller or equal than 3 over 4 pi plus 2k pi. So we said this. And now we have to put this solution in a graph. Okay, so we have minus pi over 4, we have 3 over 4 pi, and then we have to put all of the periodicity, so 7 over 4 pi, etc., and then if we want 11 over 4 pi. Okay, then we have to do the graph. We have to do the graph of the sign. So we know that the function is positive between minus pi over 4 and 3 over 4 pi. Then also between 7 over 4 pi and 11 over 4 pi. And here it is negative, and here it is negative, and here it is negative, and then it continues because it is a periodic function, so it will become positive, then negative, etc. Okay, this means that this function decreases, then increases, then decreases, then increases, then decreases, etc. So, in 3 over 4 pi, there is a local maximum. In 7 over 4 pi, there is a local minimum. In 11 over 4 pi, there is a local maximum, but we can include it with the periodicity. There is a periodicity of 2 pi here, between 3 over 4 pi and 11 over 4 pi, so there is a periodicity. Okay. So there are infinity local maximum and infinity local minimum. Okay, so in our graph we have 3 over 4 pi, 7 over 4 pi, and this function achieve a local maximum here and a local minimum here. I don't know the value, we can compute the value if we want. So f evaluated in 3 over 4 pi is equal to 2 times the sine of 3 over 4 pi is the sine of 3 over 4 pi is my square root of 2 over 2. And the cosine is minus square root of 2 over 2. Conversely, in 7 4 pi is 7 over 4 pi, the sine is negative and the cosine is positive, so with the minus it is a negative sign. Okay, this means that we have here 2 square root of 2 and here minus 2 square root of 2. Okay. So here 2 square root of 2, we can put here. Okay, so 2 square root of 2 here, minus 2 square root of 2 here. In 0, but in 0 it is not important what the function does, but if we want to do a good graph also here, the function is in 0 is minus 2. Okay, so its value is here. So the function does something like that. Okay, and it is periodic, so the graph is always the same. This means that this is a global maximum, and also this is our global maximum, because the value is the same, because the function is periodic, and also here and here. So x equal 3 over 4 pi is a global maximum point, plus 2k pi, because we can put all the periodicity, and 7 over 4 pi is a global minimum point, with all the periodicity if you want. Okay, I think it was the tangent line on the function. Okay, so this was the first exercise, and now we continue with okay, we continue with the second part. Find the tangent line at the function, this function, in the point x0 equal to 1. So the function is e to 1 minus x over 1 plus x squared plus x 3x to the 4 minus 1. So the tangent line at this point. So the equation of the tangent line is the following one. So it is y equal f of x0 plus the derivative at x0 times x minus x0. So in our case x0 is 1, we have to compute f of x0 and the derivative of at x0. So f of x0, it is f of 1, and it is e to 1 minus 1 times 1 plus over 1 plus 1 square plus 1 3 times 1 to the 4 minus 1. E to 1 minus 1, it is e to the 0 is 1. 1 over 1 plus 1 is 1 half, plus 1 times it is useless. Then 3 minus 1, it is 2. 1 half plus 2, so 5 half. Okay, this is f of x0. Now we have to differentiate this stuff and then evaluate the derivative at 1. So the derivative is just, we have to differentiate the first function. So we have 1 plus x squared because it is a ratio, so we have to put the denominator square. Then the derivative of the numerator is, it is an exponential, so we have to differentiate the exponential, and then we have to multiply times the derivative of the argument, of the exponent, and this is 1 minus x. The derivative of 1 is 0. The derivative of minus x is minus 1, times 1 plus x squared times the denominator, minus the derivative of the numerator without derivation, e to 1 minus x, times the derivative of the denominator is 2x. Yes. Plus, now we have to differentiate this product. So, the derivative of the first is 1 times the second without derivation, plus the first times the derivative of the second. So the derivative of minus 1 is 0. The derivative of this is 12. 3x squared x to the 4 is 12x cubed. Okay, this is the derivative. Now we have to compute this derivative at x equal to 1. Okay. Then we have just to substitute 1 here, and we obtain 1 plus 1, it is 2, 2 squared is 4. Then we obtain e to 1 minus 1, it is e to the 0, it is 1. 1 times minus 1 is minus 1. So minus 1 times 1 plus 1, it is 2, minus e to 1 minus x, it is 1, times 2 times 1, it is 2. Okay, and that's all for the denominator. So it is better to write here over 4. Plus 1 times 3 minus 1, it is 2. Okay. Plus 1 times 12. Okay. So we have here minus 2. Minus 2 is minus 4. Minus 4 over 4 is minus 1. Minus 1 plus 2 is 1. 1 plus 12, it is 13. Okay, so now we have computed all. We just have to substitute here the results we obtained. So f of x0, it is 5/2 plus the derivative at x0 is 13 times x minus 1. So it is y equal 13x minus 13 plus 5/2, and if we want to write it better, we can compute this. Minus 13 is 26/2 plus 5, it is 13x minus 21/2. Okay. Okay, so also this exercise is concluded. Okay, then we do the first study of the function. So f of x is equal to logarithm of x over x. Okay, not here, but here. So we have to analyze domain, asymptotes, and maximum and minimum. I study also the sign because I think that with the study of the sign, the study of the function becomes easier, and you can get more information that will help you in the study of the asymptotes, for example. but this is not necessary, so you can avoid the study of the sign of the function if you want. Okay, now we start analyzing the domain. Okay, as regards the domain, we have that x should be different by 0 because different from 0 because x is at the denominator, and then x has to be greater than 0 because it is the argument of the logarithm. So in general, x has to be greater than 0. Okay, it is useful to draw immediately in the right side of your page the Cartesian plane and put the information of the function step by step. So we obtain here a first information. The domain is x greater than 0, so we can erase this part. Okay, perfect. Then this is the domain. Then I want to study the sign of the function as second step. So the logarithm of x over x greater than 0, greater or equal than 0. Okay, this is a product, so I can multiply by 0 here, because in this case we know that x in our domain, x is greater than 0, so I can multiply by 0, and there is no problem doing that because x is greater than 0, I don't have to change the sign. So in this case I can avoid the study of the sign of the fraction. Okay, so the equation becomes logarithm of x greater or equal than 0. I pass to the exponential, so e to logarithm of x greater or equal than e to 0. E to logarithm of x, you remember by the fundamental rules that it is equal to x. So x greater or equal than 1. This is the study of the sign, so I have 1 here. I do just a straight line here, just to say that when x is greater than 1, the function is positive, so I erase this part. When x is smaller than 1, the function is negative, so I erase this part. Okay, now, asymptotes. So, in order to study asymptotes, the behavior at the limit, we have to understand which are the limit where we have to study this behavior. The limit are given by the domain. So x greater than 0, this means that we have to study the limit when x converges to 0. I put just 0 plus because in 0 minus the function is not defined of the logarithm. And then the second limit is when x converges to plus infinity. No minus infinity. Minus infinity no, because the function is not defined at minus infinity. So in this case I study just the limit at plus infinity. Okay. So when x converges to 0, we have the logarithm of 0 is minus infinity over 0 plus, and the result is minus infinity. Because minus infinity over 0 is infinity. So, in order to understand the sign minus infinity or plus infinity, you can do minus over plus, it is minus, or you can say, in this case it is simple, but when it is complicated, the study of the sign gives you an help, because you know that the limit has to be infinity, and you know that in 0 plus the function is negative, because I erased this part, so the function cannot go to plus infinity, and the result has to be minus infinity. Okay, here the limit logarithm it is an indeterminate form if you want, because the logarithm goes to plus infinity, x goes to plus infinity, but taking into account the hierarchy at infinity, the logarithm loses against x, so the result is 0. So we know that this function goes to minus infinity here and goes to 0 here. Okay. It has to be from decreasing and not increasing, so from the x positive and not the x negative, because we have studied the sign. Okay, then we can start studying the derivative. Okay, so the derivative of this function. It is easy because it is just a ratio, so we put the denominator square here. And here we have the derivative of the logarithm. It is 1 over x times the denominator minus the derivative minus the numerator without derivation times the derivative of the denominator, which is just 1. So we can simplify here, and we obtain the derivative is 1 minus log x over x squared. Okay, and this means that we have to study now the equation in order to study the increasing and decreasing intervals. This equation, 1 minus log x over x squared greater or equal than 0. Also here, I can multiply by x squared, because x squared is positive in our domain. It is positive always, and it isn't equal to 0 because x is strictly greater than 0. So I can multiply by x squared here and simplify, and I obtain my equation 1 minus the logarithm of x greater or equal than 0. Okay, this means minus logarithm of x greater or equal than minus 1, so logarithm of x smaller than 1, by changing the sign and the verse, and this means 1 it is logarithm of e, this means x smaller than e. Okay. So, the derivative, I write here. So the derivative is positive when x is smaller than e, and the derivative is negative. We can do strictly positive and strictly smaller. It is equal to 0 when x is equal to e, and it is negative when x is greater than e. This means that the function increases, reaches here, this is 1, we have e here, it reaches e, and then it decreases. Okay, this graph is ugly, okay, perfect, and it starts decreasing here. Okay, so this is, in E we have a local but also global in this case. So x equal to E is local and global maximum point. And this is the graph of the function. So the function increases because the derivative is greater than 0, reaches a maximum point which is e, and then starts decreasing, approaching 0 because the limit is 0. Okay, this is a standard example of the study of a function. Okay, but I think we can do also a limit just to conclude this part. Okay, the limit is limit when x goes to 0. So limit when x goes to 0 of e to the x minus the square root of 1 minus x over sine of 2x. Okay, so we start substituting. E to 0 is 1, minus the square root of 1 minus 0 is 1, over the sine of 0, 2 times 0. This is 0 over 0, so an indeterminate form. We know that now you studied a very useful tool to study this limit, to solve this limit, and it is the L'Hopital rule. So the rule of the L'Hopital, which says you that in order to solve an indeterminate form like that, you can differentiate, derivate the numerator, derivate the denominator, and then study the limit of the derivative. Maybe it can be better, maybe it can be worse, but we can try. So we can try computing the derivative of the numerator and the denominator. You have to remember that you can use the L'Hopital rule just when you have an indeterminate form. If you don't have an indeterminate form, then you cannot apply the L'Hopital rule. It is useless, because if you don't have an indeterminate form, the limit is solved, because you know what is the value of the limit. But in general, it can appear that in the previous test, some guys solve the limit without checking if there is an indeterminate form, just computing using the L'Hopital, and maybe the limit it is not an indeterminate form, and so the result it becomes different, because the L'Hopital fails if there is not an indeterminate form. So first check that you have an indeterminate form. If there is not an indeterminate form, the limit is solved, you know the result. If there is an indeterminate form, maybe you can try the L'Hopital. The L'Hopital can work, in some case works, in some case doesn't work, and you have to do a different way. So maybe using, collecting the faster term, or using some known limits, non-fundamental limits. But here we can start trying the L'Hopital. So the derivative of the numerator. Using the L'Hopital, we have that, we can say that we use the L'Hopital here, writing this, or better, the limit of our function is equal, applying the L'Hopital to this limit. So the derivative of the exponential is the exponential. The derivative of the square root is 1 over 2 square root of the argument times, because it is a composite function, times the derivative of the argument, which is minus 1. Okay, over the derivative of sine of 2x. The derivative of the sine is the cosine of 2x, times the derivative of the argument, because also this is a composite function. So the derivative of the argument is, the derivative of 2x is 2. Okay. Then, the limit when x converges to 0, we do some calculations, some computations. So minus and minus becomes plus, 1 over 2 square root of 1 minus x. And here 2 cosine of 2x. Okay, now we try to substitute. Maybe the indeterminate form disappear now. E to 0 is 1, plus the square root of 1 minus x is 1. So 1 plus 1 over 2. Okay, so the indeterminate form is disappeared, because if the numerator is different from 0, so if the denominator is different from 0, the result is a number. If the denominator is 0, the result is infinity. But the indeterminate form disappears, so the L'Hopital work. And here, the cosine of 0 is 1. 1 times 2 is 2. So this is 3 over 2 times over 2. This is 3 over 4. And this is the result of the limit. Okay, so in this case, the L'Hopital works. Okay, so I give you an example. In the second exercise, for example, okay, we have 2x minus 3x squared over the logarithm of x when x converges to 1 plus. So, if you maybe it is better to erase before, because we need also the we need more than one line. Okay, so the limit was limit when x converges to 1 plus of 2x minus 3x squared over logarithm of x. Okay, if you substitute, you obtain 2 minus 3 over the logarithm of 1 is 0. So this is minus 1 over 0. Well, the logarithm of x minus 1 is a negative number. 1 plus, 1 minus, it remains negative because it is far from 0. The logarithm of x, when x is greater than 1, the logarithm of x is greater than 0. So in this case we have 0 plus. Minus 1 over 0 plus is minus infinity, because 1 over 0 is infinity and the sign is minus. Okay, so in this case there is no indeterminate form. The limit is solved without do nothing, just substituting. Okay, we have to pay attention because here the L'Hopital doesn't work. Because if we apply the L'Hopital, it is wrong to apply the L'Hopital. If you apply the L'Hopital here, you obtain the limit when x is greater than 1, it converges to 1 plus 2. The derivative of this is 2 minus 6x over the derivative of the logarithm is 1 over x. If you substitute now, you obtain 2 minus 6 is minus 4 over 1. So minus 4. Which is obviously different from minus infinity. So, if you apply the L'Hopital, you obtain a wrong result. Why? Because you don't have an indeterminate form. So, if you start applying the L'Hopital and not checking not substituting and checking if there is an indeterminate form, you do a mistake. You do a mistake. So first check if there is an indeterminate form. If there is an indeterminate form, you apply the L'Hopital. If there is not, you don't apply the L'Hopital. Okay, perfect. So I think we have done for now. We solved the two limits, this and this exercise, and also the exercise of the midterm of last year. So I think it is good. And see you next week.